Hello everyone, my name is Sakshi and in this video we are going to solve problem number 46 on LeetCode, which is given an array nums of distinct integers, we have to return all the possible permutations of that array. We will follow these three simple steps to solve this problem. Firstly, we will look at the recursion tree for this problem. After that, we will implement the algorithm and then we will discuss the time and space complexity of our algorithm. Let us first look at the recursion tree. I have drawn the tree for a specific example of 1, 2, 3. How do we find permutations of an array? Let's name this array A. So if we start from index 0, then for every index I greater than or equal to 0, we will swap A of I with A of 0 and then we will apply this permutations function recursively for the second element and then for the third element and so on. So here, let's look at this. We are starting from index 0. We are swapping A of 0 with A of 0. So we get 1, 2, 3. A of 0 with A of 1. We get 2, 1, 3. Then swap A of 0 with A of 2. We get 3, 2, 1. Now for this layer, we are done and we are done with index 0. Now going on to index 1, we will swap A of 1 with A of 1. We get 1, 2, 3 and then swap A of 1 with A of 2. We get 1, 3, 2. Now similarly 2, 1, 3 and here we are swapping 1 and 3. We get 2, 3, 1, 3, 2, 1 and swap 1 and 2. We get 3, 1, 2. And these are the 6 permutations of the array which we need in our solution. We are done with the recursion tree now. Let's look at the implementation now. I am going to write a recurse function. Look at the inputs. This is the given array, size of the given array, current index, and the final output vector in which we will be storing our permutations. Now, according to our logic, we will move from index to n and we will swap nums of index with nums of I. Then we recurse for index plus 1. And after that, we have to swap again to get the original array. Look at this. When we are at 1, 2, 3, we swapped 2 and 3. We get 1, 3, 2. Now we have to swap back because we want to reach 2, 1, 3 as well. So we swap back, we reach 1, 2, 3, and then we swap back because here we swapped 1 with 1. So we swap back, we get 1, 2, 3 again, and then we go in this tree, in this subtree. So that is why we need to swap back. Now, when will we store nums into RET? When we reach the last element. That means when index is n minus 1, then we push nums into RET and we return. To call this function, I'm getting the size of the array, defining a vector, output vector RET. Now I'll call recurse nums n. We'll start from index 0 RET. And I'll just return RET. Let's run this code. It works fine. We are good to go. We are done with part 1 and part 2 of our process. Now let's jump to the part 3, which is discussing the time and space complexity of this algorithm. Let's first discuss the space complexity. So we are not using any extra space here. RET is just the output vector, but we are using the space for storing the recursive calls, which is the space used by the recursive stack, which is order n by this tree. So the depth of this tree is n, which is the size of the array. So the space complexity of this problem is order n. Now let's discuss the time complexity, which is the number of recursive calls into the time complexity of one recursive call. So what is the time complexity of one recursive call here? Time complexity of this line is order n because the size of nums array is n. And the time complexity of this for loop is also order n in worst case. So the total time complexity of one recursive call is order n. Now we have to find the number of recursive calls. For that, look at this. There are 3 calls on the first level, 3 into 2 calls for the second level, which can be generalized as n calls for the first level, n into n minus 1 for the second, n into n minus 1 into n minus 2 for the third, and so on. It goes till the last number is 2, because here the last number is 2. So it goes till n into n minus 1 into n minus 2 and so on up to 2, which is n factorial. So the total number of calls is the sum of all these numbers. Clearly, the last term is n factorial. All the other terms are less than n factorial, and the total number of terms are n minus 1. Since we want to calculate the big O of the number of recursive calls, we can say that the number of recursive calls are big O of n minus 1 into n factorial, which can be further called O of n into n factorial. So the total number of recursive calls are n into n factorial, and time complexity of one recursive call is order of n. So we can say that the total time complexity of the recurse function, this recurse function, is order n square into n factorial. And we are calling this recurse function here. So we can say that the total time complexity of permute function is also order n square into n factorial. If you face any difficulty in understanding any segment of this video, I would suggest to have a look at my previous videos on subsets. Also, I have added the link to this code in the description below. If you like this video, please like, share, and subscribe. If you have any doubts or comments, please leave them in the comment section below. That's it for today. See you in the next video. Bye-bye.